Hello, this is Mrs. Nearing, and in this video we're going to talk a little bit about Ka, Ksp, and pH. These are some different applications of equilibrium systems where we can use our previous knowledge about the equilibrium constant K and ice charts in order to make some predictions. And if you were here in class last week, we actually took some measurements to test out our predictions. So this is related to what you will find on page 17 in Unit 7 of your OneNote. So the first equilibrium system we're going to look at is a solubility product constant, Ksp, and we see this kind of equilibrium system when you form a saturated solution. And a saturated solution is one where any additional solid added to the solution will no longer dissolve. You will notice you have a saturated solution, or you can tell your solution is saturated if you see some solids still remaining on the bottom of the beaker. So that tells you not all of it dissolved. At this point, the rate of solid dissolving into ions is the same as the ions sticking together and reforming the precipitate. So we often might look at it and say, oh, look, it's not dissolving anymore. And that's sort of true, but it's kind of also not true. What's really happening is, like if we look at this example here of lead chloride, when it's saturated, some of the solid lead chloride particles are dissociating to form these aqueous ions. But at the same time, some of those aqueous ions in solution are coming together and reforming the precipitate. So the rate of dissolving is equal to the rate of precipitation. So notice how this reaction looks like the exact opposite of the precipitation reactions that we wrote back in Unit 4, right? Sorry, my handwriting is messy right now. So it's the exact opposite. So it turns out that that is an equilibrium system too. Those things we were writing as one-way arrows can actually be thought of as two-way arrows. Okay. And when we reverse a reaction, make another little connection here. When we reverse reaction, the K value is inverted. So the K value of this reaction would be 1 over the Ksp for that solid. Okay. The other system we're going to look at is the acid dissociation constant, which we call Ka. And acids are substances that dissociate into ions when placed in water, forming H+ ions. So when one of the ions you form is H+, that substance is an acid. And when the equilibrium described involves an acid dissociating, we call the K expression a Ka, where the A stands for acid. And here is a generic form for an acid. In this case, the A- is just a generic form for anion. That could be any anion. So the anion could be nitrate. It could be a monoatomic anion, such as fluoride. It could be something more complicated, like C2H3O2. So it's just some sort of anion. It could be monoatomic, polyatomic. Okay, so that's in general what your acids are going to do. And here's a side-by-side comparison of Ksp and Ka. Notice how they look kind of similar. They're both dissociation. So over here on the left, we've got something dissociating into ions. Over here on the right, we've got something dissociating into ions. Some differences you'll notice is with a Ksp, the reactant is always a solid. And that's important because remember, we leave solids and liquids out of the K expression. So when you look at a Ksp value, you'll notice there will not be a denominator. So you don't divide by anything because the reactant's a solid, it just gets left out. Over here with your acids, your acid reactant is aqueous, so you do have, it does show up in the K expression, you will have a denominator. And with your Ksp, your reactant is a solid ionic compound. With your Ka, your acids are typically molecular covalent compounds. And one of the products is always going to be H+. That's what makes it an acid. An acid are things that generate H ions when you put them in water. So that brings us to this, thinking about the idea of pH. And acids and bases are something you're introduced to in regular chemistry, and we talked about them very briefly in, I believe, Unit 4 this year. But a general overview for right now, and we'll get into much more detail with this. But acids are something that generate H+ ions when dissolved in water, and acids have a low pH, less than 7, Bases generate hydroxide ions when dissolved in water, and they have a high pH. And there's some equations on your equation sheets that can be useful when calculating, that we can use to calculate pH. And we'll find there's a relationship between pH and something called pOH. And notice how when you put a P in front of something, there's also something called like a pKa, which is the negative log of the Ka value. And you might start to notice a pattern here. When you put this P in front of something, that just means you're taking the negative log of the value. So the pH is the negative log of the H concentration. The pOH is the negative log of the OH concentration. And it turns out that in an aqueous solution, so when you're dissolving stuff in water, the pH and the pOH add up to 14. So those are values that we will use in this lesson, and we will use it a lot later on because our next unit is acids and bases. Whoop, excuse me. Okay. So let's take a look at our first system. We've got calcium hydroxide, and we're going to make a saturated solution of calcium hydroxide and measure it. So this is our equilibrium reaction there. So first thing we're going to do is we're going to write a Ksp expression for that. So Ksp is products over reactants, and then coefficients become exponents. So the 2 becomes an exponent, and we leave out solids and liquids. So we're going to leave this out of your K expression. Okay. Now I want to set up an ice chart in order to predict the amount of ions I'm going to form when I make a saturated solution. So here you see I copied and pasted the reaction. And since solids and liquids are not included in the K expression, I'm going to leave them out of my ice chart. I like to draw a wiggly line. You could just leave it blank, whatever you want to do. And what we're doing here is we are going to take some solid calcium hydroxide, and we are dissolving it in a solution that's pure water. So you want to imagine, like initially, before we dissolve the calcium hydroxide, how many calcium ions are present in the water? Well, that number should be 0. Okay, because it's just going to be pure water. Same with the hydroxide concentration. We're going to say that it's 0. Turns out, we'll find out later, there actually is a tiny amount of hydroxide present, but we can ignore it. It's negligible. Okay, so we're going to say these start at 0 because we've got pure liquid water to begin with. And then we are going to, as my calcium hydroxide dissolves, I'm going to make some calcium ions and some hydroxide ions. And remember, they react in a 1:2 ratio, so your change row has to reflect that. And if you think about predicting the direction of change, notice how initially, if we calculate our Q value by plugging these 2 values into our K expression, our Q is 0, and that means Q is less than K, therefore the reaction is going to proceed right and make more products. So I know that this is going to be a positive value. And then equilibrium is initial plus the change. So there we go. And now I'm going to go back and plug that into my K expression. I'm going to use a different color here instead of the red. Okay. So if I go back to my K expression, calcium is X. OH is 2X. I'm going to square it. Make sure to remember to distribute that squared there. So this becomes 4x squared times x. So that is 4x cubed equals 5.5 times 10 to the negative 6, because in this case we're given the K value. So x equals the cube root of 5.5 times 10 to the negative 6 divided by 4. And just so you know, the way I like to sometimes type in cube root into my calculator, like if I want to take the cube root of x, sometimes I just type that in as x raised to the power of 0.33. Depending on how you use your calculator, sometimes you might find that a little easier. So, and if you were to take the square root of something, you can type it in as x to the 0.5. So those are equivalent if you want to use that trick. When you do this, you should end up with x is 0.011, and the units of that are in molarity. And the reason why I know that is because whenever you use a Kc expression, the values are always in molarity. If it were a Kp, the values would be pressures in atmospheres. And those are your only 2 options. So notice this one, we're using square brackets. This is a Kc expression. So my answer is going to be in molarity. But I got to make sure that I answer the question. The question says, what's my concentration of hydroxide ions? And my hydroxide ion concentration is actually 2x. So my hydroxide concentration is actually 0.022 molar. So that's my final answer. So notice I've used my ice chart and my given K value to predict the amount of hydroxide ions I should form. Okay. So keep that in mind, it's 0.022. Now I'm going to go over here and I'm going to use these equations to calculate pH. So what I know is my hydroxide ion concentration is 0.022. So if I look at these equations, it looks like this one's useful. This is the only one that involves hydroxide ion concentration, so let's give that one a shot. So my pOH is the negative log of 0.022 molar. And I'm going to stop and plug that in my calculator. Depending on what kind of calculator you have first, you might type the log first, or you might type the number first, then hit log. So just, double check that. And this is going to be 1.65. And you might be thinking to yourself, she's got too many sig figs in here. We'll go over the log rules, or sig fig rules for logs later in acids and bases. Turns out the rules are a little bit differently. When you're looking at a log value, it's just the numbers to the right of the decimal that are significant. So when I write 1.65, that actually only has 2 sig figs in it. And the reason why is this one right here. You can think of it as telling you like the order of magnitude. So like if we were writing a number in scientific notation, actually let's look at this number right here. I would look at this number and say it only has 2 sig figs in it. Right? This number right here is telling you the order of magnitude. So we don't count that as one of our sig figs. That just tells you whether your measurement is in the tens place, the hundreds place, the thousands place. That's what this number right here is doing in a pH or a pOH. So just FYI, we'll go over that again later. So your pOH is 1.65, and then I'm trying to find pH. So this equation looks useful. So my pH is 14 minus the pOH. So 14 minus 1.65. And as far as sig figs goes, this 14 I'm going to assume is like, infinite number of zeros behind it. So this is going to be, 12.35 is my predicted pH. And then if you were in the lab, we actually took some calcium hydroxide and put it in some water, stirred it around, took the pH, and we measured the pH. And a lot of people got something pretty close to 12.35. I took a picture of a sample set of data that I collected. In this one, I got a pH of 12.17. So, pretty close. Okay, so pH should definitely be in the 12s. Notice how you can tell this solution is saturated because it is not clear, so it's not transparent. That means there is still solid present. And if there's still solid present, that's a clue that the solution's saturated. So you've dissolved as much as you can, and there are going to be some leftover solid present. All right, so now I want to see what happens. What if we dump in some calcium chloride? So we had some calcium chloride kind of pellets there, and that is a solid. So first you want to ask yourself, is calcium chloride soluble? If you remember our solubility rules, the main ones were the alkaline metals are soluble, nitrates are soluble, and then your chlorides are soluble except when it's bonded to silver, lead, or mercury. Those were your exceptions. So this is a chloride, so chlorides are mainly soluble unless it's bonded to silver, lead, or mercury. It's not, it's bonded to calcium. So yes, we expect it to be soluble. And when it dissolves in water, what will it do? Well, it's going to, since it's an ionic compound, it is going to break apart into ions. So it's going to form calcium ions and chloride ions. And then if you look back at our original reaction, which I need to rewrite here because you can't see it, this was our original equilibrium system, right? We're looking at calcium hydroxide dissolving. And then you want to ask yourself, are any of these ions present in this equilibrium? And yeah, it looks like we have something in common here, calcium ions. So when you dissolve calcium chloride in water, what you are doing is you are adding calcium ions, which are a product. So now your system is no longer at equilibrium. You have too many products. So as a response, your reaction is going to shift left. And that means, like, what does shift left mean? Shift left means you use up the products, which is the excess calcium and those hydroxide ions in solution, and then you form the reactant, which is solid calcium hydroxide. That's what shifting left means, right? Using up products, making reactants. As that happens, we're going to use up products, right? So that means the amount of hydroxide ions is going to decrease because they're being used up to form more reactant. And now I got to think back to our definition of acids and bases. Remember we said that bases have make hydroxide and they have a relatively high pH. So the more hydroxide there is, the higher your pH is. So if you decrease your amount of hydroxide, you're going to decrease your pH. And you could also get into some mathematical reasoning with the negative logs and stuff, but this might be the easier way to think about it. So we expect to see the pH go down. And then we actually did that in the lab, and I have a side-by-side of our data. So over here you see what pure calcium hydroxide looked like, had a pH of somewhere above 12. If you add calcium chloride to it, we notice the pH drop. In my case, it dropped down to 11.7, which is a pretty big drop because pH is a logarithmic scale. So going down by what, like 0.4, that's a pretty big difference. And your change in pH is going to depend upon how much calcium chloride you added, but you should definitely notice a decrease. And then we looked at our second system, which is a Ka. We looked at citric acid, and let's write the Ka expression for it. Remember, a Ka expression, it's the same thing as a Kc expression. We're writing it the same way we've done before. It's products over reactants. Coefficients become exponents. So let me start writing that down. And then this is kind of a long one, so it takes a little while to write out this formula. Okay, so there's my Ka expression. And then we want to set up an ice chart to determine the H plus ions. And if you want to, sometimes when I rewrite my reaction, I just use an abbreviation. So I'm going to do that here. Use an abbreviation instead of writing out that long polyatomic ion. Okay, so my initial concentration of acid is 0.1. And I put some acid in some just pure water. So this is going to be 0 to begin with. And notice how we're starting out with a Q is 0. So the reaction is going to proceed to the right to form more product. So we're going to use up reactant and we're going to form product. So this is what our ice chart looks like. And I'm going to go back and plug that into my Ka expression. So I end up with x times x, so that's x squared, divided by 0.1 minus x equals 7.4 times 10 to the negative 4. And at this point, to solve this, it looks like we might have to use the quadratic formula. But remember, we have that handy kind of simplification we can do, where if K is 3 orders of magnitude smaller than your initial concentration, then you can say the change is insignificant. So let's look at what that means. Okay, so our K value is 10 to the negative 4. Our initial concentration, might help to write this in scientific notation, is 1 times 10 to the negative 1. That's how I'd write 0.1 in scientific notation. So it looks like this exponent is 3 smaller than this one. So we're just barely hitting our cutoff where we can use this simplification. So what that means is since K is sufficiently small here, we can say that 0.1 minus x is basically just 0.1. Basically, we're saying the value of x is so much smaller than 0.1, then we can just ignore it. We can just ignore that change. So that makes this math a lot easier. It becomes x squared divided by 0.1 equals 7.4 times 10 to the negative 4. So you end up with x being the square root. I'm going to plug this in my calculator. Okay, so we've got Um, and then we've got that by times 0.1. So it's the square root of 7.4 times 10 to the negative fifth, because you're going to multiply these two things together. And if you take the square root of it, where is that on my calculator? You should end up getting that x is 0.0086 molar. And notice x is your concentration of hydrogen ions. So, cool. So let's go on the next slide and let's calculate pH with that. So we figured out earlier that x, which is equal to our hydrogen ion concentration, is 0.0086. And we want to find pH. So it looks like this equation is going to be the useful one. So pH is going to be the negative log of 0.0086. So that should be 2.07. And again, this number has 2 sig figs in it. So it's just the digits to the right of the decimal that are significant. Okay, so then we want to actually make this solution first, then we'll test the pH. So to make a solution, first from a solid, first you have to figure out how many grams of solid we should weigh out. So we want to make 50 mils of this 0.1 molar citric acid, and we're given the molar mass of it, few, because that would be a long one to calculate. Cool. So we have a molarity and a volume. So our first step is to find moles. So moles is molarity times liters. So your molarity is 0.10. Remember, molarity is moles per liter, right? And then your volume is, we got to convert that to liters. So notice how liters cancel out. So that's why molarity, that's why moles is molarity times liters. Thinking about dimensional analysis and units there. So this is how many moles of citric acid we need. And then to find mass, you want to take your moles and multiply it by your molar mass, 2.10 times 1.5 grams per mole. So here notice moles cancel. And then 0.05 times 210.15. It should be 1.05 grams. Did I leave out a zero? So 0.005 times 210. Yeah, I think I left out a zero the first time. All right, should be 1 gram about. Cool. And when you want to make a solution, pause the video for a moment and read through these options. Which glassware should you use to make a solution? This is something you could be tested on, so you want to think about it. Okay, the correct answer for what you should use to make a solution in is a volumetric flask. I'll show you a picture of that on the next slide. And when you make a solution in a volumetric flask, what should you add first, the solid or the water? So pause and think about that one. The correct answer is you want to add the solid first. And the reason is the way solutions are defined, or the way molarity is defined, is you want its moles per volume of the entire solution. So you want to make sure that the volume of the entire mixture adds up to 50. So you want to add the water first, add the solid first and then the water to make sure the total volume of water plus solid adds up to 50. If you start out with 50 mils of water and then add some solid on top of that, you're going to end up with the volume bigger than 50 and you won't know what it is exactly. So you always want to add the solid first and make sure your total combined volume adds up to 50. All right. Remember from the previous slide, we predicted our pH would be 2.07. So let's take a look at how we make the solution. So we weigh out 1.05 grams using a balance. And then notice how we're going to stick it in the volumetric flask. There's your volumetric flask there. Okay, and then we're going to add water to it. That's just my squirt bottle right there. The best way to do it would be to fill up water maybe to about halfway and then stop and swirl it around to make sure the solid's dissolved and then fill it up the rest of the way to that line. So that line means you got exactly 50 milliliters. And then you pour the solution into a beaker and put your pH probe in there and notice the pH is 2.4. So yeah, pretty close, somewhere in the 2s there. And this is our last thing we're going to do, is we're going to take this solution of citric acid and we're going to add another solid to it and see if we can see an equilibrium shift. Okay, so the solid we are going to add is this guy right here. And shoot, looks like I need to rewrite my equilibrium system. So we started out with our original citric acid is H3C6H5O7 and is going to dissociate to make H plus, because that's what acids do. They break off and form an H, and then whatever is left. So if you're wondering, how do I figure out the formula of my anion? You just take the thing you started with and remove an H from it. That's all you gotta do. So cool. So this was our original equilibrium system that was described earlier. And what we're going to do is we're going to take some of this, which is sodium dihydrogen citrate is the name of it, and we're going to place it in water and see what it does. So first thing you want to think about, is this going to be soluble? The answer to this is yes, because it contains an alkali metal. Okay, so it is going to dissolve in water. And then you want to think, well, what ions will it form? So something to keep in mind in here, if you ever see more than 2 elements in an ionic compound, that means you must have a polyatomic ion present. And there are a few polyatomic ions that we memorize, but there are so many more out there in the world. You can't memorize them all. You don't need to memorize them all. What you want to do is you just want to say, oh, look, that's an awfully big ionic compound. There must be a polyatomic ion in there. And just look for the ion that you're familiar with, and then you say, okay, the rest of it must be some big polyatomic ion. So like in this case, we've got this big old formula. Maybe I've never seen this before, but I do recognize sodium. Hey, sodium I know. Sodium makes a +1 ion. So one of my ions is sodium. The rest of it, H2C6H5O7, this must be just one big polyatomic ion. And, well, I don't know the charge of this ion, but I do know that 1 sodium plus 1 of these is neutral, because I can see that over here. It looks like this thing is neutral. There's no charge written by it. So if sodium has a +1 charge, that means this big old thing right here must have a -1 charge. So I've identified this polyatomic ion without having to, memorize it. And then when I do that, I might notice, hey, this is actually the same ion that is up here in this equilibrium system. So when I add this solid to the solution, really I'm adding this H2C6H5O7 ion, which is a product. So you are going to be adding product. And when you add product, the reaction is going to shift left to use up that excess product. So shifting left means using up product and making reactant. And if we're using up product, that means we are using up H+. So our H+ ions are going to decrease. And if you think about our definition of acidic, we said that acids make H+, and that acids have low pH. And it turns out the more H+ you have, the lower the pH is going to be. So if you have less H+, then your pH is going to be higher. So because you can think of it as you are less acidic. So your pH is going to approach 7. It's going to get closer to 7. Remember, it started out at 2, so it started very low. So now it's going to get closer to 7. So now we're going to try that. We're going to add some solid to your solution, and let's do a side-by-side. So it's like initially our pH was 2.4. Afterwards, the pH is 3.1. Remember, again, that's a pretty significant difference because this is a logarithmic scale. So we saw a pretty big change in our H+ concentration. Okay, so the pH went down, so that means our H+ amounts went down. All right. Well, thank you for listening. Please get in touch if you have any follow-up questions with this.